Okay, so we are looking at representation using FOL. So let us focus a little bit on properties. So we have said of course that we can think of properties as also categories. So we did that when we looked at the example of for all x man x implies mortal x, where of course men we can think of as a category or a kind of things or a type, whereas mortal is kind of a property of people, right, or there is a property of human beings that it's men who are mortal essentially. But we sort of approximated this by saying that we can think of mortal also as a set, because that is all FOL allows us to do, and then we are saying that the set of men is contained in the set of mortal entities essentially. But there may be other choices as well. So let us look at this example of the ball is red. How do we express this in FOL essentially? Now obviously I could have said all balls are red or something like that, just to be similar to the statement we had about men and mortality, but it is basically the choice of predicates that we are talking about here so much, not so much about the quantifiers. So we could have said in a similar sense that we have a set of red objects, and let us say we have a set of blue objects as well, and this ball, let us say I am talking about a particular ball called B1 happens to be in this set. So I could express this as this fact. Likewise I could have said another ball B2 is also red and the third ball B3 is blue, which means it belongs to the set of red things, B2 belongs to the set of red things and B3 belongs to the set of blue things. And I would have expressed this as follows, that red B1 or red B2 or blue this is like saying mortal Socrates, mortal Peter, mortal Suresh and so on and so forth, where we think of the properties red and blue as also categories, and you are simply saying that okay, this element falls in that category essentially. But there is another way of looking at things, which is that supposing I had a set of colors essentially, and this set contained things like red, blue and so on and so forth, all the colors that I could have essentially. And then I could say that this ball, I have these 3 balls B1, B2, B3. So this is my larger domain, something like this. And now I am saying that there is a relation between B1 and this object red, B2 and this entity red, and B3 and this entity blue. So you see the difference between these two ways of representing things. In the first way, red and blue are unary predicates, and therefore we give them B1 and B2 and B3 as arguments, and then we say that B1 belongs to this set of red things, B2 belongs to this set of red things and so on. So this notion of red, now as a person who is interested in knowledge representation, you may be sort of curious to know that is that a right way of representing the notion of red essentially. What is the notion of red? It is not so straightforward to define what is red essentially. What we have done in the second case is that we have introduced something to our domain, which is a set of colors. So we are saying that colors are part of our domain essentially. So there is a set of entities which belong to the set of colors. So and red and blue are amongst them essentially. And if I do that, then you can see that the way I would write these statements is that something like color B 1 red, B 2 red, there is a totally different way of representing things. In this scheme of things, red and blue are elements in the domain essentially. Okay. And we will see that when we talk about representation, very often we want to add elements into the domain, which may not be tangible, which may not be real, which may not be really there in the domain, but we introduce them to make life simpler for us, and we will see that it happens in many cases, almost in all cases essentially. For example, if we talk about people, human beings. So, let us say a person like John, then John has a nose essentially. So, if I want to say that okay, let us say John's nose is hurt or something like that, then what do I conceptually what do I think of? Do I think of John and nose as two entities in my domain which have this relation of being hurt or something like that? But that is not really the case, because the nose is part of John essentially, right. And in some sense, if I think of John as an entity, I have no way really of thinking about nose essentially, unless I have a mechanism by which I think of all the components as real entities and putting together of them into a human being as an abstract entity essentially. So, John does not really exist in that sense, John is a sum of all his parts essentially. Now, that is a question we will come back to later again, but essentially these are questions that you have to try and answer as to what is there in your domain and how are you representing things essentially. Now, if you wanted to make certain statements like red is similar to orange, let us say as compared to blue. So, we want to define the notion of similarity essentially somehow, and maybe in some domains you may want to give a numerical value to this similarity. You might say okay, what is the level of similarity, it is very similar or little similar. So, you may want to give numbers to that. 0.9 stands for highly similar, 0.7 stands for similar but not so similar, and that kind of stuff essentially. If you want to do this sort of a thing, then you can see that obviously the second scheme of thing helps better essentially, because now we can try to define a relation between two objects essentially. Whereas, when you talk to define relation between sets red and sets blue, then it is not such a straightforward thing for us to think about. So, these are some issues that we will have to grapple with when we do representation essentially. Let us take another example. Let us say Mary gave John a book. How will I represent this statement? Again, keep in mind that we are still working with ad hoc predicates. We are saying that okay, we will invent predicate names as and when we need them and simply represent things using that. So, we can think of a predicate called give, for example, or gave if you want. You can already see that there is a problem which is occurring here, that especially when we talk about events, and which we will do that separately. But when we talk of a predicate where essentially you are transferring things from one person to another, then conceptually you are transferring things. But if you want to use give as a predicate, then what do you do if the sentence has the word gave essentially? John said he will give a book to Mary essentially, or John gave a book to Mary, or John every day John gives his dog a piece of bread or something like that. All these are different, they have different aspects to the word give essentially. And do we define different predicates for give and gave, because obviously they are different. Gave is in the past tense and give is maybe in current present continuous or something like that. Do we need so these are again questions that we need to address essentially. So, let us anyway for the timing assume that we have accepted the word give as a predicate that we are doing, and somehow we will introduce the notion of it being in the past or something later. And who are these things? So, we want to say that Mary gave something. Now, very often in the real world there may be more than one Mary essentially. So, that is another problem essentially. If you write a sentence like this, then which Mary do we refer to? So, again we will take a shortcut here, as is done in many textbooks. You will see that we will use some suffix to distinguish one Mary from another. So, let us say this Mary is called Mary 21 and this John is called John 2, and he gives and she gave him a book. How do I write this a book? That is a question I want to ask. So, you can imagine your domain has many books essentially, and somehow one book from the domain Mary is giving to John essentially. So, I could of course start off by saying that let me just use the term book here. That is the simplest way of doing things essentially. But what about because when I use the constant book, it refers to actually a specific book. Remember that in first order logic you have either constants or variables as terms or functions. In this case there is no function, but we could think of a function here. For example, we could think of a Skolem function here, which says that this is the book that Mary gave to John essentially. How do we handle something like a book essentially? Any suggestions? So, is book, like in the previous example, is read a predicate or is read a term? So, remember terms stand for denote objects in the domain, and we may add objects as and when we please essentially. So, is book a predicate or is it a term? What makes more sense? It makes more sense to say that, especially because we are saying a book, it makes more sense to say that it is a predicate, because basically we are saying that there is a set of books and Mary gave one of them to John essentially. And how do we express that now? We have to say that there exists an X such that X is a book, and let us say we are not really bothered about time at this moment. Give that is a little bit more faithful representation than by simply using book as a term, because we are not quite clear as to what that book stands for essentially. The moment we try to make book as a variable, then we will have to somehow say that this variable stands for a book, which means it is part of the set of books, which means we have to use book as a predicate essentially. Let us look at some more kind of things that we need to worry about. So, there are properties like height, weight, length, distance, and so on and so forth. You might even add, for example, color. We have already looked at color essentially to some extent. So, these are all properties: height of an object, height of a person, height of a tree, weight of an object, and so on and so forth. Now, with these kind of properties, we often associate values essentially. So, we may say numerical values, for example, Mary is 6 feet tall essentially, right. So, we are talking about height, but we could also talk about qualitative values, and we will see at some point. Sometimes we tend to think of them as fuzzy values, because they are not often very well defined. Sometimes they may be, but sometimes may not be very well defined, in which case we may say something like Mary is tall, or you might even say Mary is very tall. So, we have some properties called height, which we can give a value which is numerical in nature, and we can also give a value which is symbolic in nature, or which is qualitative, or which is fuzzy. We use the term fuzzy because it is not very clear as to what do you mean by tall. If tall is a set of people, then who is tall and who is not tall is not a crisp set essentially, because 6 feet could be tall, but 5 feet 9 inches is it tall, and so on and so forth. You at some point you have to give a threshold, and the moment you give a threshold, just below the threshold and just above the threshold, they are similar, but why are you calling one tall and one not tall. So, these are questions which are addressed by people who work in fuzzy logic and fuzzy sets and things like that. We may also want to address questions like Mary is taller than, let us say, Susie essentially. Again, in some sense this addresses the notion of tall essentially. So, what I am trying to drive at is that we have to find ways of representing things which can be used in different contexts for different purposes. So, if you have a notion of height and weight and length and distance and so on, we can try and represent that essentially. So, let us look at an idea which we have been hinting at essentially, and this idea, let us give it a name. This process is called reification, and it basically means introduction of abstract types. Types which do not really exist in the domain. Remember that the domain is basically a set, it is a set of this thing, but we want to introduce now the new things essentially. So, we are talking about types here essentially. So, let us talk about a type called length. So, in some sense length is of a type of an element, just like man is a type, cat is a type, apple is a type, and so on and so forth. We have now introduced a type called length essentially, whose elements are basically denote length in some way essentially. So, once we do that, we can kind of define functions like height, let us say Mary 21, and this is a function which denotes an element of type length. So, remember we have introduced a type called length, and now we are defining a function called height Mary. Remember that height is a function, we are talking about a function. Basically a function essentially is used to denote terms essentially. So, we are saying that height of Mary is a term. What kind of a term it is? It is a term which is belongs to a class of objects called, which are of type length essentially. So, essentially all lengths we will say that there is an abstract class called length, in which everything's length we talk about essentially. Now, things like height and length in particular has units essentially. Right. So, how do we handle units? We said Mary is 6 feet tall essentially, right. Is that the example we gave, I think. So, how do we handle things like feet essentially? Now, one way to do that is to think of feet as a function. So, I could say feet which takes a number as an argument and it also denotes an element of type length essentially. So, what are we doing? We are looking at a number 6 and then we are saying we are defining a function called feet of 6 and what does feet of 6 is? It basically denotes an object of a type length, which basically means that length is a type in which you can compare. You can say one length is equal to another length, for example, and we will see that we can also define the notion of an ordering, that which length is more than another length. We will do that shortly essentially, but basically length is an abstract entity of some kind and both the function feet 6 and height Mary 21, where Mary 21 is basically Mary here, are functions and they both return is not the right word because this is not a functional in that sense. They both point to or they both denote some objects of type length essentially. So, you can see that now if we want to say that Mary is 6 feet tall, our task becomes quite easier. All we have to say is that height Mary 21, since we are calling her, is equal to feet 6. Now, you have to go back to the meaning of this equality. When we define first order logic with equality, the meaning of equality is that both terms. So, first of all you must realize that both are terms refer to the same object. So, we have not quite defined what that object is, but we are saying that height of Mary denotes an abstract entity of the type length and feet 6 also denotes an abstract entity of the type length essentially. And we are saying that when we say height Mary equal to feet 6, we are saying that both of them are referring to the same object essentially, which is what we basically want to say, that this is the meaning of this statement Mary is 6 feet tall essentially. So, there is a length which when measured in feet has value 6 and Mary's height is basically that length essentially. Height and length and distance will all be of type length essentially. So, that is one way of seeing things. So, you can see that feet here is a function from let us say elements to objects of type length. Remember that length is a type now. Feet is also a function which takes numbers and translates them to objects of type length. So, we are in some sense moving everything to this type length and then saying that okay, we can talk about the length of Mary or height of Mary, we can talk about the length denoted by 6 in terms of feet, and then we can say that they are it is the same object essentially, or the height of Mary is same as 6 feet essentially. So, some questions that you may want to ask is how do you convert essentially. So, if you say 12 miles is so much in kilometers, then how do you write expressions to convert that essentially. So, I will read this as a small exercise. Conversion between units essentially. I remember one one puzzle which children ask is that there is a square and there is a man walking around the square, and for the first leg he takes 80 minutes, for the second leg he takes 80 minutes, for the third leg he takes 80 minutes, but for the fourth leg he takes 1 hour 20 minutes, and people are puzzled as how can that be, and so on and so forth. So, this is the kind of stuff that you must figure out when you are talking about conversions essentially. So, let us come to this example of Mary is taller than Susie. How do we represent this essentially? So, we want to find a consistent way of representing, we want to find a consistent way of talking about lengths and heights and tallness and distance and so on. We want to be able to handle different units, inches and centimeters and miles and kilometers, and we should be able to compare things. So, we should be able to take some word problem in some school algebra and arrive at a logical representation which we can solve somehow essentially. How do we talk about taller then essentially? I mean, of course, one simple brute force ad hoc way is to say that I will have a predicate called taller then, and I will say Mary taller than Susie. But this is kind of too simple, too naive, and it may not be useful enough to solve problems essentially. Having defined this notion of height, we can say that we can define the notion of taller x y. Let us say we define this in terms of height essentially. So, we can say that height x, and we can define some ordering relation between them which will stand for taller than or longer than or things like that, and obviously we are talking about in general terms. So, for all x, for all y, we say that the height of x is more than. So, we read this symbol as more than height of this thing. If let us say we are talking in terms of feet, but we can have other functions as well. Feet x in feet, sorry not x, some n in feet is greater than n m in feet, where there is a association between this and this and this and this. So, height of x is n and height of y is m, and we say that height of x is more than height of y if feet of n, which is the height of x, is in some ordering. We are still talking about some ordering, we are not yet into numbers yet, is greater than, let us say, or we want to introduce a new symbol maybe here, it does not matter. This in term we can define by saying that n is greater than m, where for a set of numbers we say we already have this relation defined, ordering. We will not necessarily go into what is the logical foundations of saying that n is 4 is greater than 3 and things like that. Maybe we will do it if we get time, but there can be a logical foundation based on this, and maybe at some later point we will come back to define as to what is the number. We have used this term very casually, 7, 8, 9 and 10. What are these things essentially? I mean, in logic terms, where do they come in from essentially? And philosophers and mathematicians and logicians have grappled with this idea for a long time. In fact, there is a story of this guy called McCulloch, who was one of these scientists about 100 years ago. He told somebody in the church, that fellow asked him what is it he want to do, and McCulloch apparently said that I want to know what is a man who may know a number and what is a number that a man may know. You can find this saying somewhere essentially. So, what are numbers essentially? So, maybe we will break off at this time, and we will take this up again in the next class, and maybe we will pay some attention to what do we mean by numbers, and you can try to think of this as to, and you must have heard about different ways of defining numbers essentially. And we will also look at an alternate way of representing Mary's height essentially. So, here we have said that Mary's height is the same as feet in this thing, but we could think of feet alternatively as a function from type length to the type number, which is a different way of doing things essentially, and we will look at this alternate way in the next class. Yeah, you were saying something. So, we can think of the function feet as taking a number and returning a type object of type. This length is an abstract type. No, we have just defined it, that we have this notion of length essentially, and once we have the notion of length, we want to define when is one length equal to another length, or when is one length more than another length, which is what we have tried to define here. But we could also alternatively say that why work with this abstract notion of length, since in the end we are comparing length, why not take length as an type and convert it into numbers using the function feet, in which case you would say something like this: feet height Mary is equal to 6. That is another way of looking, trying to define this. But the difference is that the feet is a different kind of a function here. It takes an object of type length and returns a number or points to a number essentially, and obviously this will have some ways, some things will become simpler with this, some things will become simpler with the other thing. We will revisit this problem in the next class essentially.